Hello, everybody. Woo! Welcome to Colloquium. Today we are welcoming our very own Julie Comerford. Woo! Julie is an associate professor, and with this colloquium, with this colloquium, she's going up for promotion to a full professor. Hooray. I don't actually know what that really means, but Julie does.
A lot more committee
more
work.
cash money. So Julie is a world expert in cosmic mashups in our hierarchical universe. This is what drives the evolution of cosmic structure and the growth of, oh no.
Went away.
Well, we're going to have to act this one out, huh? What?
It was
Maybe?
up there. But
Oh
it went away.
no. This is no good at all. Okay, maybe Andrew will fix this while I tell you about Julie.
I have a very simple strategy.
Yes. Hopefully
Perfect.
that doesn't happen again.
Okay. Julie is at the very bleeding edge of our understanding of the growth of supermassive black holes, galaxy mergers, and understanding them all with this brand new messenger we have, gravitational waves. Julie was previously, before coming to CU as an assistant professor in 2013, not 23. That would be a very rapid rise. She was a NSF and McDonald postdoctoral fellow at UT Austin. In addition to being a world expert in black holes, she's also produced her very own planetarium show and has done a ton of media recently to spread the glory of black holes more widely. She's also an amazing teacher and mentor to her grad students, postdocs, and pretty much all of the young faculty. So we're very grateful to have Julie. I'm really excited to hear all about black holes. Everyone, please welcome Julie.
Thank you, Erica, for that over-the-top introduction. The last time I was standing in this spot was for my tenure talk, and a couple of things have happened since then. And their names are Felix and Calvin, and I am on parental leave this semester with that little nugget, so I've just stepped out for today, one day only, to give this talk, and then I'm going to step back into parental leave life again. I'd also like to acknowledge my fabulous and extremely talented research group. This is a picture of us yesterday at our group barbecue that we had in the backyard. And throughout this talk, I'm going to be highlighting their contributions to all this research. And you're going to see their names in orange. Whenever you see an orange name, that's a group member, present or recently graduated alum group member. Okay, so with that, let's jump into the black holes. All right, there are lots of different kinds of black holes. I'm going to be talking about the supermassive black holes today. Those are the ones with masses of millions to billions of times the mass of the sun. Those are the ones that live at the centers of massive galaxies, so including our own Milky Way. So if you look really, really closely at the center of our galaxy, you can actually resolve individual stellar orbits. And if you watch for enough years, you can map out the orbits of these stars and surmise that there must be something very massive here that you can't see with a mass of 4 million times the mass of the sun, and so it has to be a supermassive black hole. So this is the evidence for the closest supermassive black hole to us. I'm not going to be showing data like this. Mine's going to be more like blurry. You're not going to see any more individual stellar orbits after this. Instead, you're going to see a lot of AGN. So when supermassive black holes have gas nearby them, that gas can gravitationally fall into the black hole, build up its mass, and turn that black hole into an active galactic nucleus, or an AGN. So if you take a galaxy and zoom in on the center of it, there is this accretion disk of gas swirling around the black hole, feeding the black hole, and helping it grow. And the fortunate thing about these accretion disks is there's so much energy here. There's lots of light produced across the electromagnetic spectrum. So if you're somebody who studies AGN, you can use pretty much any telescope in any wavelength regime and do something with AGN with it. So that's a great position to be in. All right, so part of the story here is, well, we have black holes, supermassive black holes at the centers of galaxies. Galaxies like to gravitationally merge with each other, and that leads to some interesting things. So here are a couple snapshots of a galaxy merger in progress from 1, 2, 3, 4, 5, 6. And I put the red dots to indicate where the supermassive black holes are. And so the first 3 panels show the early stages of a galaxy merger where the separations are tens of kiloparsec. For reference, we are 8 kiloparsecs away from the center of the Milky Way, to give you an idea of scale here. So these supermassive black hole pairs in early stage galaxy mergers, these are pretty easy to resolve. Once the galaxies start combining, the black holes get brought together to sub-tens of kiloparsec scales. These are called late-stage galaxy mergers when the 2 galaxies are actually kind of really mashing up and combining. The black hole pairs continue to lose energy until they form a gravitationally bound binary system. And so here's when they're finally in orbit around each other at separations less than a parsec. And eventually they lose enough energy, thanks to gravitational waves, that they can coalesce and form one more massive black hole at the center of this one bigger galaxy that we've created through the merger. And so gravitational waves are these ripples in space-time that are produced by massive objects moving through space. So what I always tell my class is anything with mass in the universe that's moving creates gravitational waves. So if you just go like this, like you're making gravitational waves. Like they're teeny tiny, hard to detect gravitational waves, but you are. So if you want to create gravitational waves that you have any hope of detecting, you want something really massive going really fast. So supermassive black hole, I mean, it has supermassive in the name. So that's nice and massive. And they get going really fast when you have 2 that are orbiting each other. So they can create some big gravitational waves that are still really hard to detect, but that we have hope of detecting, as I will show you later in the talk. OK, this is a bunch of pictures. Let's watch a movie. This movie is from the illustrious cosmological simulation. So this is a simulation of galaxy formation and evolution across the entire history of the universe. This movie is only going to show you one small box of the simulated universe. This box is 1 megaparsec on a side. On the left is the starlight, and on the right is the gas. And this movie is starting at redshift 4, which is when the universe was 1.5 billion years old, and it will evolve all the way until redshift 0 today. And so as we watch this movie, you can see galaxies are merging. And as galaxies are merging, you can see on the gas side, there's lots of gas being driven in towards the center of these mergers. So tidal torques funnel the gas in towards where the black holes are and ignite the black holes as AGN. So galaxy mergers are a great way of getting the gas where it needs to be if you want to light up an AGN. Oh, and then we do the spin move, just to give you the full perspective on the universe. And we keep on merging. And so now instead of thinking about what the gas is doing, I want you to imagine black holes at the center of each of these galaxies and think about what the black holes are doing as the mergers progress. And sometimes they pass each other by, and it takes a little while for gravity to pull them back together. Another spin move into the merger, where the 2 black holes will finally be brought together to form a binary and create those gravitational waves. And this movie also emphasizes the importance of the merger-driven evolution of the universe, because we started out with a lot of smaller galaxies, and by the end here, as we approach redshift 0, we're ending up with one big, massive elliptical galaxy. So galaxy mergers are big drivers not only of the growth of black holes and AGN, but also in the growth and evolution of galaxies themselves. And you'll hear more about the illustrious simulation later in the talk. So the main theme of the talk today is going to be how do supermassive black holes grow in mass? So there are 2 main forks, ways that they do this, that I'll be talking about today. One is as they accrete the gas around them and become AGN. And the other is when the black holes form binaries and merge with other supermassive black holes and produce those gravitational waves. So I'll start with the top one here, supermassive black holes becoming AGN. OK, so if we want to talk about AGN and how important that is to black hole growth, the first thing we should do is go out and find some AGN. And so traditionally, the way this has been done in spectroscopic surveys of galaxies is you have a galaxy, you take a single fiber, you place it at the center of the galaxy, you collect that light, you make a spectrum. Then you look at that spectrum, look at the emission lines, look for signatures that there's an AGN there. Okay, great. But more recently, there's been a new technique called integral field spectroscopy, which means that instead of just getting one spectrum of the center of a galaxy, you can pepper the entire face of the galaxy with lots of different spectra and get a more complete picture of what's going on in your galaxy. And so original Sloan and a lot of the original spectroscopic surveys did this technique of a single central fiber spectrum. And now with the advent of integral field spectroscopy, we're getting a different picture on galaxy evolution with this kind of more complete spatially resolved map. And the reason that spatially resolved spectroscopy is important is because you'll get different spectra depending on where you are in the galaxy. If you're at the center of a galaxy, you might get a spectrum that looks like this. If you're somewhere else in the galaxy, you can get a spectrum that looks totally different. So to get a more complete picture of what's going on in your galaxy, it helps to have these spectra coming from all across the face of your galaxy. So the largest integral field spectroscopic survey of galaxies is called MANGA. This is a Sloan 4 survey. It just completed its final catalog of 10,000 galaxies and released it last year. So this is 10,000 galaxies relatively close by, median redshift 0.03. And these hexagons kind of show you the field of view that MANGA uses to place spectra all across and build spatially resolved maps of these galaxies. Okay, so what you can do is take each spectrum, and it's like a fine art. You look at the emission lines, you look at which ones are there, you look at their ratios of strengths, you kind of like do some stuff, and you make a map that looks like this that tells you what the source of each emission line is in each spectrum. So this is a spatially resolved map of what's producing the spectra in this galaxy. And so the AGN emission is the yellow parts. The blue parts is emission produced by star formation. And then the pink parts, don't worry about too much. That's liners, low ionization nuclear emission line regions. They're like a mix of things. Some of them are weak AGN, some of them are shocks. You have to do more work to suss them out. But just worry mostly about this is star formation. This yellow stuff is AGN. So if you were observing this galaxy with the traditional way that original Sloan did it, you take one spectrum right here. You'd say, OK, those emission lines tell me it's star forming. Is star formation producing that spectrum? No AGN here. I'm going to move on. But with the integral field spectroscopy, you see a more complicated picture that there are some signatures of AGN that's just off nuclear. And so the AGN can ionize and produce these emission lines further out from just the center of a galaxy. So, are these real signatures of an AGN out here that we just can't see in the center for some reason? So I found a bunch of galaxies that look like that in MANGA, and I wanted to find out if they had AGN or not. So I observed them with the Chandra X-ray Observatory, because the X-rays are good, high energy indicators. They will tell you if there's an AGN there or not. And every one I looked at, there was an AGN at the center of the galaxy. So the Chandra X-ray observation showed that there was an AGN here, even though from the single fiber spectrum, you would have passed it by and said no AGN. And there are lots of reasons why there were no AGN signatures just at the center. And I kind of broke it down galaxy by galaxy, but the main perpetrators were sometimes there's an AGN here, but just the star formation signatures are stronger, so it kind of drowns out your AGN signature. Sometimes there's an AGN here, but there's lots of dust obscuring it. And sometimes there's an AGN here, but AGN kind of flicker on and off. And so if you happen to catch it where the AGN is off right now, but it used to be on, so there's some remnant emission out on the outskirts, you can get this sort of signature too. So when I added it all up, if you use single fiber spectra alone, you will be missing half of the AGN that you could get that are there in these galaxies with traditional methods. And that kind of stopped me in my tracks, because that's a factor of 2. And a lot of people built a lot of science out of the original Sloan observations in their AGN catalogs, and it was only telling half the story, and probably a biased half of the story. So this inspired me to write an NSF proposal. So this is a new project I want to do to delve more deeply into how to use integral field spectroscopy alone, like if you don't always have Chandra, to use just this to figure out if there's an AGN there or not. So for example, is the AGN emission count more if it's closer to the center? How many spaxels count? Like if you do other line ratios and look for shocks and things, like what combination of things you can do with just the integral field spectroscopic data can you do to build a more complete census of AGN and catch all these things that you're missing? So another thing that we did with MANGA was look for coronal emission lines. Coronal emission lines are high ionization potential lines, so that means they could be a really good signature of AGN, because AGN are very energetic. But coronal emission lines are weak, and so they've been poorly studied. Most papers have like samples of 10 or fewer coronal emission lines. So they seem like a good AGN indicator, but they haven't been studied in a statistical sense. And so that's where Jimmy Negus came in with his PhD thesis. He built the largest sample of coronal line galaxies using MANGA data, because that data was so deep. And here are his galaxies and then coronal line emission maps. And some of the coronal emission lines were nuclear, and some of them were off nuclear. And so we wondered whether these galaxies actually host AGN. So we got approved for some Chandra observations that are coming in to use X-rays to tell us if they're actually AGN. And we're particularly curious if the off nuclear ones still have AGN or not, or if there's any delineation between these two camps. And to zoom out for the kind of broader picture of why coronal emission lines are important is there's a lot of coronal emission lines in high redshift galaxies. JWST is detecting coronal emission lines. And so we would like to do this kind of lower redshift study to understand them better so we can apply them to higher redshifts and help find high redshift AGN. Okay, and the last thing I want to say about this is all this MANGA work is a direct result of this department buying into Sloan 4 and making that financial investment so that we could have early access to the data and do this stuff before anybody else. So thank you for, thank you for buying into Sloan 4 so we could do this MANGA stuff. All right, so that's a little bit about finding AGN. Now let's talk about how the AGN get their gas in the first place. Because you find AGN in all kinds of galaxies, merging galaxies, isolated galaxies, and there are kind of two main ways that AGN get their gas. If you're in an isolated galaxy, then the gas can just accrete, can just fall in directly from the bulge or from cosmic filaments and get into the black hole that way. If you are in a galaxy merger, as we kind of saw in the movie that we watched, those galaxy mergers can drive tidal torques into the gas, and so the gas falls onto the black holes, and you can induce AGN that way too. And so it's been hotly debated, like which of these two is the main way of fueling AGN. And like there's so many papers, I had to go to small font, and then this is only a tiny fraction of all the papers. And everyone writes papers about it, and no one agrees. There's no consensus about whether mergers are the important thing or not. And the reason there's no consensus is that there are many confounding factors. It's not as simple as merger versus non-merger. It's, well, does it matter what stage the merger is? Are you talking about early stage mergers with large separations? Are you talking about late stage mergers? Have you thought about whether the AGN in your sample are dust obscured or not? Because when you're driving gas onto an AGN, you're also driving dust. So a lot of the AGN in mergers are dusty and can be missed by a lot of observational approaches. And then there's also merger type. If you have two big equal size galaxies merging, that's called a major merger. Or if you have one big galaxy and one little one, that's a minor merger. And they do different things in driving the gas as well. So there are all these different confounding factors you have to take into account to answer this question of what's the main way to drive gas onto an AGN. And I'm just going to focus on one here, which is merger stage. So merger stage has been one of the least studied aspects of this. And so this is the thing that my group has spent a lot of years focused on, is unfurling the dependence of merger stage on this problem of AGN fueling. And our motivation is that when you run simulations of galaxy mergers, the simulations tell you that merger stage is really important and that the AGN are usually activated in the late stage galaxy mergers. So the late stage, those are the ones where the black holes are separated by fewer than 20 kiloparsec, not the large separation early stages. Late stages, that's when all the gas is really getting into there onto the black hole. So the prediction from simulations is clear, but the observations haven't really tested this because it's hard to find AGN in late-stage galaxy mergers. Those get to be small separations that are hard to resolve, and so there haven't been the sample sizes. So our group has spent a lot of time on building large enough catalogs of AGN in late-stage galaxy mergers that we can actually test this in a statistical sense. And so by filling in this missing piece of does merger stage matter, we can use that to help answer the question of what's the main fueling mechanism of AGN. Is it mergers or is it stochastic fueling outside of mergers? And so the answer is that AGN are preferentially triggered in mergers, but only certain kinds of mergers. So all the confounding factors do matter. And so we approached this problem using lots of different galaxy surveys. We used some Hubble surveys, Sloan Digital Sky Survey, we used MANGA. And the reason we use lots of different things is that each survey has its strengths and its weaknesses. So if you kind of look at each one individually and then aggregate it all, you get the more complete picture of what's going on. And so this is taking lots of different papers that my group wrote, and I've summarized this all down to like one statement and one result that combines it all, which is that AGN are preferentially triggered in late-stage mergers of similar mass galaxies where there's a lot of dust at the center. Okay, so let's break that down. And Scott Barrows made this great plot of the AGN excess. So this is your AGN excess in mergers compared to isolated galaxies. So if there was no excess, then your data should fall along this dashed line. That would mean that mergers in isolated galaxies are equally likely to trigger AGN. And then the x-axis shows the separation between the black holes. So this is the early stage, large separation mergers, and then this is the late stage, small separation mergers. And so a couple things jump out is that there is an excess amongst the red dots. The red dots are the dust-obscured AGN. So there's a bigger AGN excess in mergers of dust-obscured, dusty AGN than the non-dusty blue ones. And that excess jumps to, what is this, a factor of this is like 30 or 40 in the latest stages when those black holes are getting really close to each other. And for major mergers, which that's not shown in this plot, but that's another result that came out. So the complete picture then is that when you're in a galaxy merger and your black holes are coming close together, that's where all the gas is that's been driven in during the merger. That's where all the dust is. So it's going to be a dusty environment in the late stages, and that major mergers, two big galaxies, bring in the most gas and get that gas to the center most efficiently. So the most efficient place to make an AGN and build a black hole's mass is in these dusty late stage similar mass galaxy mergers. Okay, so this is unraveling the dependencies of merger stage, mass, dust. And then the next thing we want to unravel is redshift dependence. How does this fueling mechanism of AGN change with redshift? And especially because redshift 2 is interesting, because that's when all the action is happening. That's when most AGN are being lit up around redshift 2. Most galaxy mergers are happening at redshift 2. And so we want to test this out to redshift 2 and beyond with JWST. And that is a proposal that Scott is writing for Wednesday. Because I'm sure many of us in this room are thinking about Wednesday. So thank you for being here 2 days before that deadline. All right, so let's take a moment and kind of pause and collect on what we've learned so far. So we've talked about supermassive black hole growth as they accrete gas as AGN. We've talked about, in order to have a complete picture of this, you need to have a good census of AGN in a couple of different ways we've been looking at to build a more complete census of AGN using integral field spectroscopy and potentially using coronal emission lines. And then we've talked about how certain types of galaxy mergers are the place where AGN are preferentially fueled at factors of 10, 20, 30 more than you would find AGN activity in an isolated galaxy. So we're starting to unravel that picture. And this type of stuff, this is the stuff I really built my career on. This is the stuff I'm kind of most known for. But after getting tenure, I felt a little bit of space. I felt like I had a little bit of breathing room. And I felt like I could start slewing. And I wanted to slew towards gravitational waves because I was so amped by the LIGO detection of gravitational waves. But those are stellar mass black holes. Like, kind of like, you know, kind of small for my team. So I want gravitational waves from supermassive black holes, but those had not been detected. But they are on the horizon as promising things that could be detected. And I wanted to be there, and I wanted to be ready for that. So the second half of this talk, we're going to start digging into supermassive black holes merging with each other and creating gravitational waves. So I'll start with a little bit of background on the background. All right, so we've got our two galaxies. They each have a supermassive black hole. They merge. They bring the black holes together. The black holes form a gravitationally bound binary. They start producing gravitational waves. Now imagine that scenario is happening all across the universe at all different cosmic epochs in time. So you have a black hole binary over here. You have a black hole binary over here. You have one that happened 5 billion years ago over here. And imagine the superposition of all the gravitational waves from all those binaries across the universe. And you can start to imagine overlapping waves from all these supermassive black hole binaries. And the way I like to picture it is space-time as like a quiet pond. And then you take a pebble and you throw it in. And that's your supermassive black hole binary. And it creates these ripples across the pond. And then you throw in another rock, a bigger one maybe. And then you throw in a smaller one 5 minutes later. And you end up with this pattern of overlapping ripples from all the supermassive black hole binaries that have been and are currently and used to be going on in the universe. That's what the gravitational wave background is. So the gravitational wave background was predicted to exist from general relativity. Now notice this subtle shift from the gravitational wave background to the gravitational wave background because it is there, and it was detected in a big announcement from Nanograv and all the other pulsar timing arrays just this summer. So the gravitational wave background has now been detected. This is the first indication of gravitational waves from supermassive black hole binaries. Like, this is the thing that the LIGO got me amped for waiting for. And so when I decided to start slewing towards gravitational waves, I realized I didn't know anything about it, and maybe I should hire somebody who does know something about it. So I put out an ad for a postdoc who was in that world, and I hired Joe Simon. And our first phone conversation, we started talking about project ideas before he even moved here. And at one point he just stopped and he said, "So I want to tell you something, but you're not a member of Nanograv." So I ran away and I became a member of Nanograv. And then I ran back and he said, "We detected the gravitational wave background." And that was in 2020. So it took 3 years of Joe and like all the people who've been working on pulsar time arrays for decades to like do the careful checks and double checks and like coordinate with the other pulsar time arrays before everybody felt good about announcing it to the world this summer. So we've been kind of like holding on to this secret, me only for a few years, the other people for much longer, I'm sure. But that gave us some time to kind of do the stuff to get ready for when the big announcement would come. And so just to give kind of a quick overview, super quick overview of what pulsar timing arrays are, it is using the very regular pulses that you get from pulsars as cosmic clocks. So these pulses come to Earth very regularly, but if there's gravitational waves in the way, then maybe they'll come a little bit earlier or a little bit later. And you can look for those time delays correlations between all the different pulsars you're keeping track of to make a measurement that, oh, there's something there, and here's how big it is, and here's what we think produced it. And so they detected this gravitational wave background that's consistent with being produced by supermassive black hole binaries. So in the press releases and things, they always call it like a galaxy-sized observatory because we're using like the pulsars as like the edges of our telescope. And I always think they say that too fast because it's a galaxy-sized telescope. Like, just let that, we're using the galaxy, all the stuff that's happening in the galaxy as our telescope to detect this gravitational wave background that's everywhere from emerging supermassive black hole. It's too much. It's too much. You can see why I wanted to slew in that direction. Okay, So now that it's here, the gravitational wave background is here, we can do all the astrophysics with it. And so that's what we've been gearing up for. Okay, so the gravitational wave background is produced by binary supermassive black holes. So in order to figure out what the amplitude and shape of the gravitational wave background should be, that's going to depend on how often are galaxies merging, the things that bring the black holes together in the first place. What are the masses of those black holes? That'll tell you something about the amplitude of the background. And how long does it take those black holes to go from binary stages to coalescence? And so we have observational constraints on the galaxy merger rate. We can go out and look and say, that looks like a merger, and count them. We have ways that we can estimate the masses of the supermassive black holes observationally. And now, yay, we have the gravitational wave background as an observation. The only thing we don't have any observational constraint on is the binary evolution of the black holes. We don't know how long that takes. We don't know what the physics are that drives it. And that's because supermassive black hole binaries, these are like sub-parsec separation black holes in faraway galaxies. Like, we can't spatially resolve that. And so people work really hard on finding binaries and binary candidates. It's really hard work. But there's really no or very limited observational constraints on that binary evolution. So let me focus in on all the question marks in the binary evolution for a moment and expand on that. So this graphic is kind of showing you like a time progression from right to left of the merger, where the red dots are the black holes. So at kiloparsec scale separations, the galaxies are merging, they're well separated. This part of the merger is driven by dynamical friction with the surrounding stars, carries away the energy, so you can actually get the galaxies together, get the black holes together. This part we understand and we derive in grad galaxies, on my favorite day of grad galaxies. Then you form the binary. This is the part with all the questions, so I'll skip that for a minute. But then when you get to the tiny, tiny separations, that part's cool. We have general relativity. We know that gravitational waves should be able to carry away enough energy at that point that the tiny separation binary can coalesce. So it's this part. How do you get the black hole binary from separations of a parsec down to the gravitational wave regime? This is the part that has all the questions. This is one of the things that Mitch is well known for posing as a problem, as the final parsec problem. So there are different ways you can get these two closer together. You could have them interact with a star in a three-body interaction, and then the star gets scattered away, carries away some energy, and brings your black holes a little bit closer. You could have the black holes lose some energy from drag as they're going through a circumbinary gas disk. These are all options that would work, but we don't have observational constraints on what the timescale is or what the actual physical mechanisms are. And so some people actually worried that maybe the black hole binaries never merged. If none of these were efficient enough, they could just like do this forever and like black holes never combine, which is horrifying because then you would not detect any gravitational waves. But we detected the gravitational wave background, so now we know they do merge. They do somehow figure out how to lose energy and get from this to this. And now that we have observations of the gravitational wave background, we can put these three things together to solve for this thing. So that is our group's goal, is to make, this has already been done. Pulsar timing arrays did the hard part of that, measuring that for us, so I'm going to just hands off with that. That's done. We're going to try to tighten these two screws as much as possible to get the best observational constraints we can on the merger rate and the black hole masses so that we can get the best observational constraints we can on this part with all the questions. OK, so let's start with the galaxy merger rate. All right, and this is work that Joe is doing. So the fractional galaxy merger rate is, if I have a galaxy, how many mergers does it have per unit time? And the observable there is how many pairs of galaxies are there on the sky. So if I see a pair of galaxies, I can deduce, like, this is going to be a galaxy merger someday. I can count up the fraction of galaxies that look like this. And so pairs, we look at their projected separation on the sky as well as their line of sight velocity separation in redshift space to make sure they're not just kind of chance project. Oh, not make sure. Reduce the odds that they are chance projections on the sky. OK, so then just because you have a pair of galaxies on the sky, they don't always merge. As you saw in that video, sometimes they kind of pass each other by and they don't come back. So we need to put in a correction factor, and that correction factor is based on simulations. So we can say what fraction of the time is our pair probably not actually going to merge and correct for that. And then the other thing that we don't know and we need from the simulations is the merger timescale. How long does it take these two galaxies to actually merge and get us to the gravitational wave regime? Okay, so that's the setup. And you might be thinking, haven't we already done this? Haven't people measured the galaxy merger rate also using Sloan galaxy pairs and done this whole approach, and we have measurements of this? And yes, we do. But those measurements are over a decade old, and there have been a lot of advances since then, particularly computationally. So we figured it was time for an update, particularly now that the galaxy merger rate is becoming elevated in importance, now that we've detected the gravitational wave background. Like, let's do this whole thing again from scratch, updated. So a couple, just to highlight a couple of the updates. Previous measurements of the galaxy merger rate used a single number for the correction factor and the time scale. It just treated all galaxies the same. Like, they all have the same odds of merging or not, and they all have the same merger time scale. And we're going to base those on either mergers of spiral galaxies with other spiral galaxies, which there are elliptical galaxies too that are also merging, but they didn't take those into account for this calculation. And then they did the merger timescale using the Millennium simulation, which you don't have to know anything just to look at the name to be like, that's a little dated. It's like, if they named it Millennium, then it was like, ooh, the Millennium's coming up. We're going to call it that. It's a little dated. It's a dark matter only simulation. No stars, no gas, no baryons, just dark matter, which is great for getting the dark matter merger rate. But I want the galaxy merger rate, and there's not a straight line you can draw from dark matter halo merger rate to galaxy merger rate. It's a messy line. So how about we redo all this using the illustrious simulations, which are the ones I showed you at the beginning. They have stars in there. They have gas in there. They have all the things to give you a galaxy merger timescale. And they also have merging elliptical and spiral galaxies that you can use to get the correction factor. And instead of just doing one number and treating all galaxies the same, we treated each galaxy pair differently. So we calculated, or Joe calculated these things as a function of pair separation on the sky, velocity offset, redshift, galaxy mass, all those things. Okay, so after all the updates, Joe found a merger rate that was twice as big as what people had been finding earlier. So that means there are more galaxy mergers happening than we thought by a factor of 2. More galaxy mergers means more supermassive black hole mergers, and that's great if you're a fan of gravitational waves, because that means more gravitational waves, stronger gravitational wave amplitude background. So we're going to take this updated result, we're going to put that in for our galaxy merger rate. And so that was all work doing Sloan, which is relatively low redshift, using galaxy pairs with Sloan. We want to go higher redshift. And this is where Amy Schechter's work comes in, is we want to calculate the galaxy merger rate out to higher redshifts too, to fully encapsulate the evolution of mergers over cosmic time. And so Amy is doing this using not galaxy pairs, but using machine learning. And so the idea is we got our trusty Illustris again. We're going to take Illustris. Here's a snapshot from Illustris. Beautiful. You can see the gas. You can see all the faint tidal features. Beautiful. Amy takes this, throws it in a mud puddle, stomps on it, like scuffs it all up until it looks like real data. And this is the real data, I mean, and this is Hubble data. So, but OK, so you lose all the beautiful things, but this is like what it would actually look like with that telescope. And then she uses machine learning to train on this, to say this is what galaxy mergers look like. And then once you train on this, you can go apply this to real Hubble data and find galaxy mergers in Hubble. And so the idea is to do this with the Hubble data out to redshift 3. And when we started this project, we did Hubble because that was like the best that there was. But now there's JWST. So we're going to like finish the Hubble stuff because it's still, but then we're going to do it all again, the same framework with JWST. And so here's your Illustris picture again. And here, after you muck it up, like it still looks pretty good. So this is the mucked up what it would look like with JWST and different filters with JWST. So the plan is, and Becky Nevin and Amy are putting in a proposal Wednesday to do this whole project and use machine learning to find galaxy mergers and data of its T. And then you can do it out to redshift 6, which would be when the universe was 1 billion years old. So then we could do the merger-driven evolution of the universe from the first billion years all the way up to today. So then you're starting to get a really complete picture of galaxy mergers in the universe, which is important not only for the gravitational wave background, but also for that. Remember the first half of the talk with AGN-driven blah, blah, blah stuff? We can do that. We can do ancient history. We can do that with these high redshift mergers too. So that's the plan. Okay, so that's what we're doing with the galaxy merger rate. We've got it. Joe's got it done at low redshifts. We're working on getting higher redshifts with Hubble and then ultimately JWST data. So let's talk next about how you get the masses of these supermassive black holes. Okay, so I showed you in like slide 1 the ideal situation. The ideal situation would be you can resolve the stars in orbit around the black hole and do some Keplerian orbits and dynamics and get the mass of your black hole really precisely. All right, this is the dream. This is you can only do this for our supermassive black hole. But for other close by galaxies, you can still use stars and gas, not individually resolved stars, but you can still use stars and gas that are close to the black hole. They need to be close within the gravitational sphere of influence, which is, depending on the mass of the black hole, kind of like parsecs to tens of parsecs in size is what you need to resolve the stars and gas to get a direct dynamical measurement of the mass of a black hole. So you can do that. That's great, but most galaxies are too far away to be able to resolve that kind of parsec scale. So what else can you do? Well, if your black hole is an AGN, then let's look at our little AGN diagram. There's the black hole. There's the accretion disk. And then there's this nifty region of blobby clouds called the broadline region. And this is within the black hole's sphere of influence. So if you can get the velocities of this, so you detect this as a broad emission line in the spectrum, and you can measure the velocity of the clouds from that and get a good direct estimate of the black hole mass from that. That's great, except most black holes are not AGN. Only about 5% are. And then most AGN, you can't see the broad lines because they're being blocked by this dusty, obscuring donutty torus around. So most lines of sight, the dust will block your view, so you have to be lined up pretty well to see the broad lines. So less than 1% of galaxies in the Sloan Digital Sky Survey have visible broad lines that you can do this with. So that's kind of a bummer too. So what's a way I could get black hole mass that I can actually do for most galaxies? You're going to have to do something less direct, like using scaling properties with scaling relations with galaxy properties. And so these scaling relations are with the bulge of the galaxy. So the bulge is this part right here. It's kiloparsecs in size, so it's bigger than the sphere of influence of the black hole. So it's not going to be a direct dynamical mass estimate, but some properties of the bulge do scale with the mass of the black hole. So you can use things like the mass of the bulge or the stellar velocity dispersion to get a less direct way of getting black hole mass. So you're going to have more errors and more biases, which is going to matter and have a big effect on the gravitational wave background that you infer. So you better be careful in what you use for your black hole mass, and you better understand the biases. So we decided to use Sloan Galaxies to compare the different options for getting black hole mass to kind of figure out, well, what's the best way forward if you can't do the great dynamical way? What's the best indirect way? And so we looked at using bulge mass to get black hole mass, and we looked at using bulge stellar velocity dispersion to get black hole mass. And the velocity dispersion is usually measured from a spectrum. Sometimes you don't have a spectrum, and so some recent work has showed that if you only have an image, there's still things you can get from the photometry that you can then use to infer a stellar velocity dispersion. So these are kind of the 3 different indirect ways that we're going to compare to try to figure out a path forward for the best way to get black hole masses. And so this is work that Maggie Huber is doing and coming to a comps near you about a year from now. But Maggie was kind enough to share some preliminary results that I could show to you guys today. So here we're using the mass, black hole mass that you get from broad lines as the truth mass like the most accurate dynamically based mass that we could get from this Sloan survey. So the broadline mass, the truth mass, so-called truth mass, is always on the x-axis. And so if your other way of getting the mass agrees with that, you should fall on this dashed line. So we're looking for what falls on this dashed line the best with the least scatter. And so if you use the mass of the bulge, then you will overpredict your black hole mass. Whereas if you use velocity dispersion, then you get these relations that fall more in line with what you would get from the broad lines. And this is the velocity dispersion you get from spectra. This has the least amount of scatter, so this is the best thing you should use if you need to do something indirect. There's more scatter if you use photometry, but sometimes photometry is all you have. And so the context for this is that in the pulsar timing array community, the gravitational wave community, people usually do this. And so Maggie's going to show that you really shouldn't do that. If you need to do something with photometry only, you should do this, do the inferred velocity dispersion from photometry instead. And the other broader context to this is that there are increasingly large photometric surveys of galaxies happening now with JWST, coming in the future with LSST. So we're not going to have spectra to always get this. So when you have a large photometric survey of galaxies, what should you use to get black hole mass? And Maggie's project is going to point everybody in that direction of what to do. OK, so let's tie it all together. So this has been measured, check. We've been working on doing the best measurements we can of this and giving the best advice we can on how to do supermassive black hole masses so that now we can pull together these three observationally based things to finally get a constraint on the time scale and the physics of supermassive black hole binary evolution. So that's the plan for the next couple years, is to do all this pulling together and to start to figure out how this works, because this has no observational constraints before. OK, so that's the gravitational wave background from like all the binaries merging. That's the time scale of the next few years. Looking even further ahead, I still really want the gravitational waves from like an individual black hole binary merging and coalescing. And that's coming in the future with pulsar timing arrays, but that's also coming at higher redshifts. We'll be able to see gravitational waves from the first black holes forming, like the small ones at redshifts beyond 10. We'll be able to detect with LISA, the Laser Interferometer Space Antenna. OK, so this is planned for launch in the 2030s. So this is like the reach thing that I'm slowly slewing towards. And OK, so this gives you some context for what LISA is going to do. LIGO's down here detecting these stellar mass black holes. The pulsar timing arrays are up here detecting supermassive black holes. LISA's right in the middle of that gravitational wave period. It can detect smaller mass, but still very massive black holes that are like the first black holes, supermassive black holes forming at the highest redshifts in the early universe. That is the space that LISA is going to fill in. And in order to detect those gravitational waves, you need really long baselines, really long arms for your interferometer. So the arms have to be so long, like you can't build anything on Earth. Like pulsar timing arrays, they use pulsars to get long enough baselines. LISA's cool enough that, OK, so the plan is they're going to launch these 3 spacecraft and shoot lasers between them. That's your interferometer. And these are going to be separated by 2.5 million kilometers, which is 6 times the distance between the Earth and the Moon. That's going to be your interferometer just like floating around in space, like waiting to detect gravitational waves from the first supermassive black holes at highest redshifts. Like, OK. So you see why I'm excited for this. This is what I've been waiting for. And so I am on some science working groups right now. We're doing the work to figure out what observations we need to do to prepare for LISA, to make sure we have all those observational things as tightened as possible to maximize the science that we get out when LISA launches and starts detecting gravitational waves. Some of the cool things LISA is going to be able to do, it's going to be able to detect supermassive black hole binaries before they actually coalesce. So you would have some time to run to the telescope and go try to find the galaxy. You could see a quasar being born. Like you could watch it happen in real time following LISA alerts. So those are the kind of things that we're preparing for in this science working group. And at our group barbecue yesterday, the topic came up of some members of my group are planning to get tattoos of their PhD thesis subjects on them, like AGN and galaxy mergers and things. I don't know if Maggie was quite there yet, but Amy, I think you committed to getting a galaxy merger tattoo. Yeah, okay, she committed to all of you right here, right now. And Jimmy was going to get an AGN. So it got me thinking, like, this is the tattoo I would get. Lisa is the thing. So I think, yeah, like the first data that come in from Lisa on like the first supermassive black hole, that's the tattoo I would get. So that's how I plan to end my career. Get that tattoo and then peace out. Okay, so to summarize what we've learned, we've talked about a couple of different ways that supermassive black holes grow in mass. We've talked about how to find AGN different ways and find the hidden population of AGN, how AGN grow in late stage massive merging galaxies. Then we've talked about how supermassive black holes grow by merging with other black holes. And we're working on getting better measurements of the galaxy merger rate. It was twice as big as we thought before. We're steering people towards a different direction for indirect supermassive black hole mass estimates. And some of us are getting super amped for the next decade with Lisa and detecting the first supermassive black holes forming. All right, thank you.
Thank you, Julie, for that excellent colloquium. I'm going to take, mic privileges here. So back at the way beginning when you were showing that manga IFU spectrum and you had the AGN signatures at these really large radii.
Yeah.
Are those like ionized bubbles that are indicative of like AGN feedback or something, or what?
Okay.
Was
I have a bonus
that?
slide for you. I feel like I'm in comps. I have a bonus slide.
Woo!
To answer that question for you. Yes. So AGN can photoionize gas out to kiloparsec scales. And so this is Becky called this the galaxy that will haunt our dreams because, oh my, it was a thorn in the side / the most exciting thing. For years, we had to get so many different telescopes on this thing to figure out what was going on with this weirdo galaxy. But so this is the pink stuff, purple stuff, that's the AGN. And then all this blue-green stuff, that's photoionized gas, like kiloparsecs out. And then there's this little like loop of stuff coming out here too. So after observing it with every telescope on Earth and not on Earth, we came to the conclusion that this is a flickering AGN, one that's turning on and off because gas gets accreted kind of in discrete events. Like you accrete some gas and you're AGN, and then there's nothing, and then you're quiet for a while, and then you accrete some more, and you kind of flicker on and off. And so this is some old ionized gas from an old episode of accretion that's still like out there and kind of shining before it dies out. This is a new loop that's coming out, and we were able to kind of compare this picture to simulations. And so this simulation of a galaxy accreting gas in this episodic way, and you can see like loops of new stuff that are flowing out and then old stuff that's still there. And this, I don't have the video, but it, you can like see the bubbles come out and then fade away and the new bright bubbles coming out. So it's stuff like that, I think, that explains some of what we're seeing in the manga observations.
That is so cool. Okay, next question. I can let other people.
Oh, thanks for the fantastic talk. I was wondering, in the calculation of the merger rate, what was the factor or factors that were biasing it to be half as much as it should have been?
Yeah, so I think it's mostly because, okay, we'll go to that. We tried to do as one-to-one approach, follow the same approach as the LOTS paper, because that's the paper that everybody uses. And they used galaxy pairs in Sloan. So we went through and used galaxy pairs in Sloan, and we found like the same pairs, as they did. So I think the biggest difference was in the simulations-based numbers. So this correction factor for how many of these pairs actually end up merging or not, and the time scale. And I think the time scale was the biggest. I'd have to ask Joe, but I feel like it was the time scale, because when you're using dark matter only simulations, which is what the previous work did, you know, there's all sorts of baryonic physics you're missing that's going to really give you some drag and change the time scales, and all the gas physics I feel like are really important. So I think that was the biggest factor in why we found a factor of 2 difference. And then I was talking to Joe, I was like, a factor of 2, you know, astronomically, like that's not that big a deal. You know, if you think about it. But then we were like, okay, but I think the bigger thing is that we did it all separately for every galaxy as a function of that galaxy's properties. Like this galaxy of this mass and this redshift and this separation gets its own correction factor, its own time scale, instead of just assuming one thing for everything. I think that's the most important part of this work.
Yeah, I just have to say that in most of astronomy, factor 2 agreement is a cause for celebration.
Right.
You know, we don't know the solar oxygen abundance to a factor of 2, and that's really an embarrassment. But that's for solar physicists. But from a stellar physicist
side. The sun's so close by. I mean, come on, you should have it. You should have it better than a factor of 2. It's the sun. It's right there.
I found really intriguing this whole last parsec issue.
Mm-hmm.
Now, if you have a late-type stellar binary, they can lose angular momentum through magnetically coupled winds.
Mm-hmm.
And, you know, maybe that's a mechanism that possibly could work. But then, you know, you're talking about these million-plus mass black holes. The angular momentum must be fabulously large. So, you know, what are maybe Mitch should answer that, but what are some of the ideas of how that last parsec works?
Yeah, so people run these very high resolution GRMHD simulations where they incorporate all of the effects and try to see how they can get those binaries to merge. And they find ways to do it. They find ways to do it. And one of the things that would be useful to know would be the black hole spins. And that's one thing with LISA we'll be able to get. So I don't want to wait that long till there's a lot we can do before LISA. I don't know, I'll be like retired. There's a lot we can do before LISA, just with the magnitude of the background, because the magnitude and the shape of the background gives you an idea of the masses of the black holes that are merging, how long it takes them to merge. There's a lot there that you can glean. You can glean not all the specific details of the physics, but you can say, does it look like it's this kind of stellar lost cone hardening where the lost cone is being filled quickly, or is it being filled more slowly? You can start to answer any of these questions. Answering any of these questions is much more than we've been able to do before. So I don't think we'll get the complete picture. LISA will help with that, but there's a lot we can do just with the gravitational wave background.
You get a very fast question.
I'll try and keep it fast, but this was really great. So great that even I could understand as a planetary scientist. So
did I keep you with the whole time?
Yeah, so the second half of your talk presented a really simple algebraic relation where you know 3 of the terms and you need to find a 4th. But obviously there are going to be huge challenges. It's not so simple. So can you talk a little bit about what your approaches might be for getting that last term and what some of the challenges might be in getting there?
Yeah, I presented the equation of a plus b equals c, but it's like a triple integral with all the stuff like I spared you from. So the challenges are okay. So the challenges are our group is focused mostly on the observational stuff that we can do. And then there's whole other groups who are working on making the simulations better to make those parts better. So we're working on this, the observational side. And I think the biggest unknown observationally that has the biggest effect on this is the supermassive black hole mass. Because that has wild uncertainties and it matters a lot to the kind of amplitude that you're going to get. And so Maggie's work is just the tip of the iceberg on that. Actually, their initial results have inspired Joe and me to write an NSF, like 3-year kind of proposal to dig into this more. Because these scaling relations that people present are based on very biased sets of galaxies. And we're talking about merging galaxies. Maybe it's totally different. Like stellar bulges get stripped. Like maybe the mass doesn't correlate with the mass of the black hole as well anymore. And so we just kind of want to like strip it all and go back to square one with these scaling relations instead of using the ones that have been out there on very biased nearby non-merging samples of galaxies. So I think of all the things, that's what we want to dig in on the most, because that's the biggest source of uncertainty. Observationally.
Thank you so much, Julie. Let's give her one more round of applause.